This is Chapter 4 of Atoms and Elements, Section 8, Trends in Periodic Properties. We saw in the last lesson how the periodic table represents the electronic structure of the atoms, how it can show you how the electrons are arranged in the energy levels. And we also talked about how the chemical and physical properties of an atom are determined by the electrons in those energy levels, and specifically by the valence electrons. In fact, one of the most interesting things about the periodic table is that none of that was known when the periodic table was originally invented, right? So when those atoms and elements were put into the arrangement that they have, it was just based on their chemical properties. It was just based on seeing how they reacted with other things and what kind of chemical and physical properties they have. And it was only much, much later that it became clear that these trends in the properties and the way that they grouped together was because of the underlying electronic structure of the atoms themselves. So in this lesson, we're going to learn more about these periodic trends in the periodic table, right? Most people, when they hear the periodic table, they don't really think too much about what that word periodic means. What it means is it has regular properties that repeat themselves and they go in sequence. Okay, so for the representative elements, which are the elements in the S and the P blocks, remember it's the elements that are not in the transition elements, and the transition elements are the D block elements. So all of the other elements, the S and the P block, are the representative elements. The chemical and physical properties of these S and P block elements are, again, determined by the valence electrons. And we saw that when you start at the beginning of any row, you're starting with the first electron in that energy level. So in the first column of the first row, you're starting at n equals 1. 1 electron in the n equals 1 energy level. In the first element in the second row, you're again starting with 1 electron in the n equals 2 energy level, and you're counting from there. In period 3, the first element begins with the first electron in the n equals 3 energy level. So since the valence electrons are the electrons in the highest energy level, then we only need to count the electrons from the first group in the row that the element is in, which means we can just look at how many columns in the element is, what group number it is, to figure out how many valence electrons it has. Okay? Now, in the new system where you count the D block electrons, we ignore the D block electrons. We ignore all 10 electrons that can fit into the D block, which means when you get past the D block into the P block on the right-hand side, the group numbers are offset by 10. Okay, so group 13 in the new system is group 3A in the old system. So when we relate the group number to the number of electrons, we want to think more in terms of the old system. Or we can think about the new system and just remember to subtract 10 from those P block elements. And then again, we also mentioned that the D block elements, the transition metals, have d electrons, like we said, and that this affects their properties in complicated ways. And so we're not really going to get too much into that. We will look at how they form ionic compounds. Metals tend to form ionic compounds, and we'll look at that a little bit, but we're not going to go too far down that road. This table is sort of a condensed version of the periodic table. It leaves out the D block elements, and it only goes up to row 4 for simplicity, so we're only going to focus on these elements for now when we consider the valence electrons. Okay, so remember, the valence electrons, we're counting in how many electrons are in that energy level. Okay, and so for these representative elements, the highest energy level is the row number. So in period or row 1, the highest energy level is n equals 1. In period 2, the highest energy level is n equals 2. In period 3, the highest is n equals 3. And in period 4, the highest is n equals 4. Okay? And so to figure out how many valence electrons there are in a particular element, we just need to count in from the first column to the element and see how many electrons there are. So let's take a random example of aluminum. Okay? So for aluminum, it's in the third row, so the highest energy level is n equals 3. So we need to count how many electrons are in the n equals 3 energy level. So we can just count columns, right? The first electron in the n equals 3 energy level is this one in the 3s orbital. The second electron also goes into the 3s orbital. And then when we get to aluminum, we see that in addition to the 3s orbital, we also have a 3p electron. Okay? So this is the valence configuration of aluminum. Okay? 3s2, 3p1. And so we can add up these numbers to figure out the total number of valence electrons. It's 2 plus 1, or 3. Okay? So this corresponds to the group number. We counted in 3 columns, which put us at group number 3A, and it's got 3 valence electrons. Now again, if we're using the new system, it's group 13 because we also counted the transition elements. So in the new system, we just have to subtract out those 10 transition elements to get 3. Okay? We don't need to do that for the first 2 columns because those are in the S block, which is before the D block. So we don't need to worry about that. But for all of these, we just subtract 10 from the from the group number, the new group number, and we get the number of valence electrons. Right? Or more easily, we just look at the number and the old group number. Right? Obviously, we drop the A. So, from the periodic table, you should be able to identify how many valence electrons there are in any element, right? And you just do it by looking at the group number. So if you look up calcium on the periodic table, you'll find that it's in group 2, okay? Group 2A, or in the new system, it's just group 2 because we don't have to worry about, it's in the S block. We don't have to worry about subtracting 10. Sometimes the 2A, again, will be written in Roman numerals like this, so be aware of that. So calcium has 2 valence electrons. Now that we know how to count valence electrons for an element, it's going to be useful to come up with a way to visually keep track of them, to draw little diagrams of the elements with their valence electrons. This is going to help when we start to combine atoms together to show different chemical bonds that form from these electrons. Okay? So the method that we use for this is, they're called Lewis symbols, or otherwise known as electron dot symbols or electron dot diagrams, because they depict the chemical element surrounded by dots to represent the electrons. So you picture the symbol for the chemical element surrounded by a box, and on each side of each of the 4 sides of the box, you can fit up to 2 electrons. Okay? So you don't, when you're actually drawing the symbol, you don't draw all the box or the empty spots for the electrons, you just draw the electrons that are there. But you should have room for up to 8, 2 on each side of the box. Okay? So to see an example, we'll do row 2 of the periodic table. So lithium is the first element in row 2, period 2. It's atomic number 3, which means it has 3 electrons in total. But if you remember the electron configuration, 2 of those electrons are in the core, which is like helium, and then 1 of those electrons is in the outermost energy level, the 2s energy level. So this is the valence electron for lithium. It only has a single valence electron. So we would write the symbol for lithium, which is Li, and then we would put a dot over it. Okay? And it doesn't really matter which side you put it on. Okay? You could also draw lithium with a dot over here, or lithium with a dot underneath, or lithium with a dot to the left. Okay? Usually you don't put them at the corners, you just put them on the sides, but either side is fine as long as you have room, you can move them around a little bit. Okay? Beryllium has one more electron, right? It's atomic number 4, so it has 4 electrons. So beryllium actually has a filled 2s orbital, okay? And those are its 2 valence electrons. So when we write the electron dot symbol or the Lewis symbol for beryllium, we need to draw 2 dots. Now it helps to remember that electrons repel one another, and so we would want to think of these electrons as being separate. Okay? We don't want to draw both electrons on the same side. Okay? Sometimes you'll see things drawn like that, especially for something like helium. You might see it drawn that way because the 2 electrons in helium both go into the same orbital and they fill up an energy level. So it makes sense to consider those as paired off. But for most other elements, we don't really pair them unless we need to. Okay, so we wouldn't draw beryllium like this, but we could draw it like this, or again, we could put them on opposite sides, or we could put one up and one to the left, right? So there are all sorts of different ways that we could write beryllium. As long as we keep the 2 electrons separate, it'll be fine. Boron is in group 3A, so it has 3 valence electrons, so we would write 3 dots, and again, we would keep them all separate. So you could do boron like that, or you could do boron like that, or you could do boron like that. These are really, oops, don't want to draw that one. These are really the only options for boron because you need one side to be blank. So you can leave any side that you want blank, but those are the only 4 options. For carbon, it has 4 valence electrons. So since there's only 4 sides of the box, each side has to get 1. So this is really the way that you want to draw the carbon Lewis diagram. And then for nitrogen, we have to start doubling. Nitrogen has 5 valence electrons. So once you put 1 dot on each of the sides of the box, that's 4. And then if you put 1 more, it has to double up one side. So you can put them both on top or both on one side, right, and have all the other sides with single electrons. Doesn't really matter which side you indicate as having the pair of electrons. It's not super important. Oxygen has 2, 4, 6 valence electrons, which means 2 of them need to be paired, and 2 of them are going to be separate. Okay. Fluorine has 7 valence electrons, and so it's going to have 3 pairs and 1 single electron. And then neon, which remember is a noble gas, and it has a filled n equals 2 energy level, has a full 8 electrons, right? All the dots on each side of the box are filled in, so it has 8 valence electrons. So you should get used to drawing these Lewis diagrams or Lewis symbols because they're going to help us sort of fit these atoms together like puzzle pieces when we create compounds. Here you can see a table that shows you these electron configurations, and it also sort of stresses or emphasizes the fact that all of the elements in a particular group have the same number of valence electrons, and so they all have similar Lewis diagrams, right? Hydrogen, lithium, sodium, and potassium all have a single valence electron, so they're all written with 1 dot. Beryllium, magnesium, and calcium all have 2 valence electrons, so they're all written with 2 dots. Boron, aluminum, gallium all have 3 dots. Carbon, silicon, and germanium all have 4. Nitrogen, phosphorus, and arsenic all have 5, and so on. Okay? All the noble gases have 8 dots around them in their Lewis diagram. So to practice this a little bit, we just want to write the electron dot symbols for each of these elements. You have sodium, atomic symbol Na, chlorine, atomic symbol Cl, carbon, atomic symbol C, and nitrogen, atomic symbol N. So to write the Lewis symbol, or the electron dot symbol, the only thing that we need to know is the number of valence electrons. And to know the number of valence electrons, all we have to do is look on the periodic table. And it's the group number, right? So in sodium is in group 1, so it has 1 valence electron. So let me write valence electrons. So sodium has 1 valence electron. Chlorine is in period 3, but it's all the way towards the end. It's group 17, or 7A. So it has 7 valence electrons. Okay. Carbon is in group 14, or 4A, and so it has 4 valence electrons. Nitrogen is in group 15, or 5A, and so it has 5 valence electrons. So now that we know the number of valence electrons from the group number, we just fill in the dots, right? Sodium has 1, so we just put a dot. Chlorine has 7, so 3 sides are going to have to get pairs for a total of 6 electrons, and then the last side is going to get a single, and that's 7 electrons. Carbon has 4, so we need to put 1 dot on each side. Remember, we don't want to double them up unless we have to. Nitrogen, you can start with 1 on each side to get 4, and then you realize that to get the 5th, you have to double it up. So I'll put that one over here. Okay. So these are the Lewis symbols, or the electron dot symbols for these elements. And it's all based just on knowing the valence electrons, which comes from the group number. Here are those answers again. Just keep in mind, if you're using the new group numbering system, that for all the p block elements, you have to subtract 10 from the group number. Okay? So chlorine, carbon, and nitrogen are all in the p block, so their new group numbers are all 10 off. So you have to take 17, subtract 10 to get 7, 14 minus 10 to get 4, or 15 minus 10 to get 5. Okay? So that's the only really tricky part about this, is remembering the difference in the group numbers. That was how you can look at the periodic trend in the valence electrons for the elements, right? The number of valence electrons just follows the group number. Now we want to look at the atomic size and the trend of the atomic size in the periodic table. The atomic size we can think about in terms of the atomic radius, which is the distance from the nucleus of an atom to the outermost electron, the electron that's furthest away from the nucleus. Okay? So this size of an atom increases as you go top to bottom within a group. The reason for that is as you go down a group, you're moving to higher periods or higher energy levels. Okay? So in the first period, the outermost electron is in the n equals 1 energy level. In the second period, the highest energy electron is in the n equals 2 energy level. In the third period, it's in the n equals 3 energy level. In the fourth period, it's in the n equals 4 energy level. And so you should remember that the energy levels get further away from the nucleus as the value of n gets higher, which means the n equals 4 energy level is much further away from the nucleus than the n equals 1 energy level. So as you go down a group, you go into higher energy levels, you're putting more electrons in, and they go into higher and higher energy levels, and so the atom gets bigger, the atomic size increases. Going across a row or a period is a little bit different. Right? At first, you might think that you're adding more electrons, and so they're getting further and further away. But in reality, all of the electrons within a period are going into the same n level, the same energy level. So all of the electrons in the first row are going into the n equals 1 energy level. All of the electrons in the second period are going into the n equals 2 energy level. All of the electrons in the third period are going into the n equals 3 energy level. Okay? So at that point, we can see that if they're all going into the same energy level, then maybe they actually all have a similar distance. But then we have to recognize something else, which is that the distance to the energy level can change depending on how strongly the nucleus pulls on it. So the more strongly the nucleus pulls on the electrons, the smaller the energy levels get, the closer to the nucleus they get. So as we go across a period, or a row in the periodic table, we're adding more and more protons to the nucleus. And so the nucleus is pulling more and more strongly on the energy levels. And so all of the energy levels get contracted in to the nucleus a little bit. And so this is why, even though we're putting electrons into the same energy level, that energy level gets smaller as you go across a period, because there are more protons pulling it into the nucleus. Okay? So the size decreases going left to right across a period. So here we can see that depicted visually. And this is a very useful picture for keeping in your mind when you're thinking about the trends of the periodic table, because many of the properties that we're about to discuss really come from the atom size. Okay? So if you can keep it in your mind that the largest atoms in the periodic table are all down here in the lower left, and the smallest atoms are all here in the upper right, it can really help you remember a lot of the trends and the other properties. Okay? So you don't have to memorize the periodic table or anything like that, but you should be thinking about it in terms of the sizes. So the larger ones are in the lower left, the smaller ones are in the upper right. Ionization energy is the next property that we want to look at in terms of the periodic table. Ionization energy is how much energy it takes to turn an atom into an ion. And you turn an atom into an ion typically by removing an electron. Okay? So it takes a certain amount of energy to pull an electron off of an atom. So for instance, if we have a sodium atom, a neutral sodium atom is going to have a configuration like this. Okay? Sodium has a single valence electron in the 3s energy level. Okay? This is its valence electron. So the ionization energy tells us how much energy it takes to remove that electron from the 3s orbital. Okay? So you take the sodium atom and you add some ionization energy. You perform work on it. You do work on the atom to pull off an electron. And what you end up with is a sodium ion, which is now positive because you've lost an electron. See, there's no more electron in the 3s orbital here. And in addition to the sodium ion, you've now pulled off the electron, and so it's separate. So we can just think of the electron as being out here all on its own. It's not part of the atom anymore. It's been freed from the atom. Okay? So ionization energy is this amount of energy that it takes to perform this process, to pull an electron off of the element. So it helps to remember, again, that the higher the ionization energy is, the harder it is to remove it. Okay? If the electron is being held very tightly in the atom, then you're going to have to expend a lot of energy to pull it off. Right? So a higher ionization energy means the electron was harder to remove. But remember that I said a lot of these properties actually have to do with the size of the atom. So ionization energy is one of these examples. Okay? If you're thinking about a positive charge being attracted to a negative charge, the force of attraction between them depends on the distance between them. So when a positive charge and a negative charge are very far apart, they don't really feel any attraction whatsoever. But when you bring them close together, they can feel a very strong force of attraction between them. Okay? An analogy that you can use is if you have two magnets, right? If you have two magnets in either hand, if they're far apart, they don't really even notice each other. But as you bring them closer together, they begin to stick together, and you begin to feel that force of attraction between them. Okay? So a positive and a negative charge are like that. The closer they get together, the stronger they stick together. Stronger they are, the more attracted they are for one another. Okay? So when we're talking about a positive nucleus and a negative electron, the electrons that are closest to the nucleus are the most tightly bound. They're the ones that feel the strongest force of attraction to the nucleus. The further the electrons get away, the more loosely they're held, the less attracted they are to the nucleus, and therefore the easier they are to pull off. So what that means is that the electrons that are further away from the nucleus take less energy to remove. They have lower ionization energies. So an atom like krypton, which has a very large radius, the outermost electron is going to be pretty far away from the nucleus, and so it's not going to be that hard to remove. So in this case, potassium has a low ionization energy. Lithium, on the other hand, the outermost electron in lithium is much closer to the nucleus than it is in potassium. So the lithium electron is going to be more strongly attracted to the nucleus, and so it's going to have a higher ionization energy. Okay, so in any group of the periodic table, the higher ionization energy is at the top. Okay? And the lower ionization energy is at the bottom. So it goes really the opposite of the radius or the atomic size. The larger an atom gets, the smaller its ionization energy is. The bigger an atom, the lower the ionization energy, right? And this again comes from these two concepts. The further away an electron is, the easier it is to remove. And the easier it is to remove, the lower the ionization energy required is. So this shows you the trend in ionization energies, in that it's got an arrow here that says it decreases as you go down, and it increases as you go across. Remember, the size going across a period is larger on the left-hand side and smaller on the right-hand side. So the smaller one is going to have the higher ionization energy. Okay? And the bigger one is going to have the lower ionization energy. Okay? Again, for the exact same reason. It's because the size of the atoms decreases as you go across the periodic table, across a row in the periodic table. So ionization energy has the opposite trend to atomic size. The bigger the size, the smaller the ionization energy. Decreases going down a group, and it increases from left to right. So what this means is that the elements that are down here are going to have the lowest ionization energy. And these are the metals. The elements that are up here are going to have the highest ionization energy. Those are the nonmetals. Okay? So in some sense, the ability or the ease with which you can ionize an atom tells you something about how much of a metal it is, how metallic it is. So that brings us to metallic character. An element with metallic character is one that loses valence electrons easily. In other words, it has a low ionization energy. Okay? It's easy to pull the electrons off of it. So metallic character is higher in metals on the lower left part of the periodic table and lower for nonmetals in the upper right. Which makes sense because the metals are in the lower left and the nonmetals are in the upper right. So metallic character is sort of just an expression of the understanding that being a metal or not isn't really a binary state, right? It's not like everything is either a metal or it's not. It's sort of a spectrum from more metallic to less metallic, right? And that was also hinted at when we were talking about metalloids, which are sort of in between the two, and the properties are intermediate between metals and nonmetals. Okay? That's because they have an intermediate metallic character. So metallic character increases going down a group and decreases going across a group, which means it directly reflects the trend in the atomic size. A larger atom is more metallic. A smaller atom is less metallic. Larger atoms have lower ionization energies and more metallic character. They're in the lower left. Smaller atoms have higher ionization energy and less metallic character, and they're in the upper right. So these are three properties that are very closely related, and they're very important for understanding how atoms interact with one another, especially when we deal with ionic compounds. This table summarizes those trends, so you can just sort of use this as a reference, right? The atomic size increases going top to bottom and decreases going left to right. The ionization energy decreases top to bottom and increases left to right. The metallic character increases top to bottom and decreases left to right. So atomic size and metallic character are the same. They both increase going down and decrease going across. Ionization energy is the opposite. It's the reverse. Okay? And then you should also remember valence electrons, which is really related to the group number. So going top to bottom within a group, you have the same number of valence electrons. All of the elements in a group have the same number of valence electrons. As you go across a period, left to right, the number of valence electrons increases. So as an example, imagine you're given the elements carbon, nitrogen, and fluorine. Which is the largest atom, which has the highest ionization energy, and which belongs to group 5A or 15? Okay, so these are all questions that you can answer just by looking at a periodic table. So here we can look at the relevant part of the periodic table. We don't need to see the whole thing. All of these are in period 2 in the P block. So for any question like this, it's important to remember that you can really only compare the size or the ionization energy or the metallic character when you have elements that are within the same row or within the same group. If you have two elements where both the group and the row or the period are different, then it can get complicated. There's not really a way to tell very clearly which wins out, right? So you can only make these direct comparisons if all of the elements are in the same period, like they are here, or in the same group. Okay? So in this case, they're all in the same period. We can see we have carbon, nitrogen, and fluorine. So the question, the first part is, which is the largest atom? Well, remember that the atoms get smaller as you go across the periodic table. So fluorine is smaller than nitrogen, and nitrogen is smaller than carbon. So carbon is the largest atom. Okay. Which has the highest ionization energy? Well, remember the ionization energy is the opposite of the size. So the larger the atom, the smaller the ionization energy. The smaller the atom, the higher the ionization energy. So if we want to know which has the highest ionization energy, it's the one furthest to the right. It would be fluorine. Okay? It's the one that's the least metallic. That's another way of thinking about it. And then the last question is very straightforward, which belongs to group 5A or 15. You just look at the group numbers, and you see this is 5A in Roman numerals, or 15 over here. So that's N. Okay? That's very simple. Now we can just complete these sentences, fill in the blanks with either decreases or increases. So going down group 6A or 16, the ionization energy blank. Well, going down any group, the size gets larger, right? As you put electrons into higher and higher energy levels, the sizes get bigger and bigger. So if we're going down a group and the size is getting larger, then the ionization energy must be getting smaller. It's decreasing. Going across period 3 from left to right, the atomic size decreases. Okay? So going from left to right on the periodic table, the atomic size gets smaller. And that is because as you put more protons into the nucleus, it pulls the energy levels closer to itself. Going down group 2A or group 2, the metallic character, well, if we're going down a group, we know that the metals are in the lower left, so if we're getting further down, then we must be getting more metallic. So that means that the metallic character must be increasing. Right? Metallic character increases.